I just want to welcome you to the fourth day of this nice STRANU workshop. We are all here in Trento. Unfortunately not, but hopefully this will be the case in the next occasions. And we have in this session 3 talks, the 3 of them in the very same topic about hypernuclear physics. I think we can start. The first speaker is Nir Barnea, and please, the stage is yours.
So thank you very much, and I surely hope that in our next meeting, we will be able to meet either in Trento or somewhere else, really together and not through the Zoom. In my talk, I'm going to discuss single and double lambda hypernuclei in an approach we developed over the last few years using what you call a baryonic effective field theory. This is a work that I have done together with Avram Gal, Bezalel Bazak, and Martin Scheffer. The 3 of them are now in Jerusalem. Lorenzo Contesi, that is now in Saclay, but when we started this project was also with us in Jerusalem, and Iji Maresh from Prague. We addressed in our approach, first of all, S-shell hypernuclei, specifically the overbinding problem of lambda helium-5. Then we moved to study double lambda hypernuclei and also to the study of continuous state, namely resonances. The last topic will not be covered in this talk, but we will cover it after the coffee break by Martin Scheffer. So let me give you 4 slides that all of you are familiar with, which are our propaganda slides. So we have many known nuclear isotopes. We have 2 orders of magnitude less known states of lambda hyperons, and we have another magnitude less cases of double lambda hyperons, which are these yellow points. And this points to one fundamental problem in the field, which is the scarcity of experimental data. Then when we study the spectrum and binding energy of lambda hyperons in heavy nuclei, we see such beautiful spectra, which I took from Avram's signature talks, and you will probably see it again in an hour from now. And also this beautiful slide that gives you the spectra of lambda hyperons over many nuclei and many energy levels. So this is a beautiful example of the shell model when we consider single lambda states. Of course, there is a larger picture, and in the larger picture, we can ask ourselves, okay, what is the role of hyperons, or specifically lambdas, not only in light nuclei or in bound nucleus, but also in macroscopic objects like neutron stars. And there was this, I would call it famous work that by Londoni et al., by the Tendo group, that showed the importance of 3 body forces in stiffening the nuclear equation of state, aligning experiment and theory regarding the binding energy of lambda hyperons and giving stiff enough equation of state, which are consistent with recent measurement of massive neutron stars. So this was for the motivation, and now let me go a bit to the details. So we wanted to write an effective field theory for lambda hyperons, and there are a few challenges that we face when we try to carry out this program. The first and clear is that we have only limited scattering data, out of which there is no real low energy data. Now it's starting to emerge, situation is a bit changing with femtoscopy, femtoscopy experiments, but until very recent, we had no real low scattering data. There are very few known bound states in the S-shell hypernuclei, and so far we have no resonance data. Also, we have some open issues, or used to have open issues in this field. We have now contradicting results about the lifetime and binding energy of Triton hydrogen 3 lambda or Triton lambda. We have the issue of charge symmetry breaking. This was solved by the works of Gazda and Gal. We have questions such as what is the onset of double lambda binding? What is the lightest hypernucleons with 2 lambdas? And what is the stability of lambda and n system, etc., etc. So, as an example, this is the lambda n scattering data. What we have is 2 very old, almost older than me, experiment by Alexander and Zeki Zorn from the 60s. And also, these data are not really low energy data. They are actually too high to our taste when we need really low scattering parameters like effective range and scattering length in order to derive our theory. However, now there are new venues to get data. One is, of course, femtoscopy, which brings in new and fascinating results, and the recent calculations by the AlQCT mainly of lambda n and other hyperon interactions. So this is the input problem, or part of the input problem. Now let me just give you an example of a situation that we have seen a couple of years ago regarding the ability of the theories to predict the binding energy of lambda helium-5. So the experimental result is 3.12 MeV, and all the theories that we have seen at the time were over-predicting, over-binding this system with typical energies of 4.5 to 5 MeV. The only result which we found that was consistent with the experimental data was one of the Monte Carlo calculations, but the price paid for this nice agreement regarding lambda helium-5 was that a hypertriton was not bound. So the situation was that we had no predictions or no good theories able to properly describe all the S-shell hypernuclei. So in order to address this problem, we devised what we call bionic EFT, and let me now spend a few slides about the theory. So the basic idea of nuclear effective field theory is that, okay, we know that the fundamental theory is quantum chromodynamics, which is formulated in terms of quarks and gluons. However, if you don't want to do lattice calculations, you would like to replace this low energy, these degrees of freedom with low energy degrees of freedom, such as the baryons and the mesons. If you do that, you're in theory, which in general we call higher effective field theory, although it can be more general than that. And when you integrate out the mesons, we are left with a theory which is consistent only with the baryons as our degrees of freedom. And what I'm going to discuss in this talk, I'm discussing in this talk, is a theory where our degrees of freedom are the nucleons, which are neutrons and protons, and the lambda hyperons. And in general, our Lagrangian will contain the kinetic energy terms for the nucleons, for the lambdas, and interaction terms, where the interaction terms are in essence in this theory always contact terms, which can include either just contacts or derivatives of the fields, which is more or less equivalent to expanding the interaction in powers of momentum. Of course, we need to regulate this theory. Therefore, we introduce a cutoff, which I denote by small lambda, since capital lambda is reserved in our case to describe the hyperon. What you have to envision that is being done here is that we take a diagram such as this fundamental diagram for lambda n scattering and this loop, which contain nucleon propagation and sigma propagation and 2 pion exchange, and we say, okay, in low theory, all the details encapsulated in this loop can be regarded as a point-light object, which we ignore its spatial dimensions. So in general, we repeat this process both, or this approach both for any interaction and for the hyperon-nucleon interaction. And now, in the nucleon-nucleon interaction, the long-range part of the force is mediated by the pion. And however, in the case of the hyperon-nucleon interaction, it is mediated by at least 2 pions. As a result, we may say that in the case of nuclear physics, our high energy scale or breakup scale is the pion mass. And in the case of hyperon-nuclear interaction, it is 2 times the pion mass. As a result, when we are considering lambda n interaction or hyperons in nucleus, we have a more favorable small parameter, which is the ratio between typical momentum, which we write as the 2 times the average binding energy for the nucleon, divided by our breakup scale. So it goes from 0.5 or 0.8 to 0.3, and our corrections are usually of the order of this number squared. So we expect to get corrections of the order of 10%. Now we can construct our theory, and we have a very simple rule. Each derivative should introduce a factor of Q over M, and each field introduces a factor of Q over M to the power of 3/2. And we just arrange all the terms in our Lagrangian, counting how many terms or how many powers of Q over M we have. So this is what one will call the naive power counting, and this is very simple, and one can arrange the theory according to these ideas. In this way, the leading order, interaction will be just a constant. The next correction, we will have terms which are proportional to the momentum square of the incoming or outgoing pair, etc., etc. And of course, we need to regularize and normalize our theory by introducing some form factor. And this was shown, this approach to be equivalent to the effective range expansion. So on the face of it, this looks like a very simple and very straightforward approach to studying any low energy system. However, when you start to apply this theory, you run immediately into problems. The first problem occurs when you move from the 2-body system to the 3-body system, and then you realize that if you include only 2-body interactions, then the binding energy of the 3-body system actually diverge as lambda square, which is the square of your cutoff, which means you have no predicting power regarding the 3-body system. This is just the famous Thomas collapse, and this problem was solved by Bedak, Hammer, and Van Kolk, who suggested that in order to stabilize the system, one must introduce a 3-body force, which means that we need to promote a 3-body term into our ground state. Second problem was that the effective range goes to 0 when we take the cutoff to infinity. Again, this is a reminiscence of the Wiener bound. This was also discussed by Phillips, Bin, and Conan. The idea or the way to solve this problem is to include all terms beside the leading order term in perturbation theory. So in principle, everything is solved. We need to take 2-body and 3-body interaction in leading order, and we need to take all higher terms in perturbation theory. So we tried this approach and applied it to study four-body systems at next to leading order, including also effective range correction. So to our surprise, we realized that the four-body binding energy was diverging with the cutoff. And we at the beginning, we thought, okay, maybe we have a problem with our numerical codes. So we started first with resonant group method, then with stochastic variational method, and then we tried it again with Faddeev-Kovofsky method. In all these approaches, we got diverging four-body binding energy, and our conclusion was that we must add four-body force at next to leading order. These are bad news, because if we were trying now to discuss S-shell hypernuclei, where we have, you think about it as a 5 and 6 body bosonic states, one can project, this is not proved yet, but it's highly probable that we will need also 5 body and 6 body forces when we go to next to leading order and next to leading order. So this theory is becoming very difficult to handle when you go beyond the leading order. So in the next slide, applying our theory to hypernuclei, I will focus only on leading order results. So in this theory, we have 2-body and 3-body terms, which are described by contact interaction. Therefore, for each channel in the 2- and 3-body system, I need what they call a low energy coefficient. I need 2 such coefficients to describe S=1 and S=0 nuclear scattering, and I need 1 3-body parameter which I can fit to the triton binding energy, and I need similar parameters for the hypernuclei. Guys, somebody is with his open microphone. Can you please mute it? Somebody is with an open microphone. Can you please mute? Thank you.
Ignazio Bombacci, you should mute now. And also Parada as the mic. Okay, now everybody's muted.
I did it, please.
Thank you very much. So in order to describe lambda n and lambda lambda scattering or interaction, we need similar terms or coefficients to describe the lambda n interaction and the n and lambda interaction, and you can count how many parameters we need for each. So we need 1 lambda lambda term, 3 lambda in n coefficients, and 2 lambda n coefficients, 1 S=1 and 1 n=0. So for the scattering data for the lambda n interaction, we can use either the experimental extraction by Alexander et al., or use different models that analyze this experiment and projected the results to the limit of 0 energy. So we can try any of these models or experimental results. Then when we go to the lambda lambda scattering, we have both LQCD predictions, and now we have, due to the photoscopy, results from the Ellis and Star collaborations, which give different extractions of the lambda lambda scattering length. We also have one analysis from Gasparian and et al. Extraction of the A lambda lambda scattering length, which is this value in red. So we have, to some extent, maybe not high accuracy, but we have reasonable estimates for the lambda n and lambda lambda scattering length. But when we go now to the 3-body terms, and we recall that we need 3 n and lambda coefficients, we see that we have a problem, because we know that we have only 1 3-body hypernucleus, which is the hypertriton. Therefore, in order to fit the other two parameters, we must go to the 4-body system. In a similar fashion, since we don't have any hypernucleus with 3 baryons and 2 lambdas, in order to fit the coefficient of lambda NN, we need to go to the 6-body system, this double lambda helium-6. So doing so, we fit all these parameters, and now we can predict, for example, the binding energy of lambda helium-5. To our fortune or surprise, turns out that if we take, for example, the Alexander B extraction of the lambda of the lambda n scattering length, we get very nice agreement for the binding energy of lambda helium-5 between our theory and the experiment. This is the binding of what you see in this graph is as a function of the cutoff. There, our prediction for the binding energy of the lambda, B lambda, in this system. And you see that our theory predicts very nicely, or agree very nicely with the experimental data. So this was reassuring, telling us that something is working nice in this theory. And now we turn to the double lambda hypernucleus. Here, of course, there is the bigger question about stability of the H baryon, which is a system composed of 2 U's, 2 D's, and 2 S, which was predicted by Jaffe back in the 70s to be stable. And of course, the possibility of deeply bound H baryon was excluded in the Nagari event, which limited this. Actually, it was excluded completely in the Nagari event. Maybe it was not completely ruled out. Okay, this was the conclusion of a recent paper by the Ellis collaboration. Anyway, utilizing the Nagari event, we have prediction. Okay, so we have a measurement for the binding energy of these 2 lambdas in helium-6 double lambda, and we can fit our 3-body parameters, the n lambda lambda term, to reproduce this Nagara event. Doing so, we can now turn and try to predict what would be the binding energy, for example, of hydrogen 5 double lambda. And doing so, this is what we get. So again, in this figure, the X axis is just our cutoff, and the Y-axis is the binding energy of, okay, it's B lambda or B double lambda. And you see that we get results which are very stable with respect to the cutoff. And we have rather large error bar. And however, we still can safely say that we predict that this hydrogen 5 double lambda is bound in our theory. Now let me just elaborate a bit what are our different error bars. So
I would ask you to elaborate just a bit because we are running out of time.
So, okay, our error bars are either numerics or input from the limits on our understanding of the scattering length of the lambda lambda and lambda n terms, and of course extrapolations to lambda to cutoff going to infinity. We can now go and ask what are a possibility to find the double lambda hydrogen 4. In this case, we get very marginal binding, and in the limit of cutoff going to infinity, we say that the chances of this system being bound is highly unlikely. So I would say that our prediction is that the onset of double lambda hypernucleus should be the 5-body system. Then we can look at the correlation between 5-body and 6-body systems, and we see that we have a very nice correlation, linear correlation between the binding energy of the 6-body and the 5-body. And with this correlation, this is again reinforcing the idea that we have a solid prediction for the binding energy of lambda helium-5. This is similar to the Tion line between the triton binding energy and helium-4. We also try to play around to see under which condition we can have double lambda neutron-neutron or double lambda neutron system bound, and we found that this is really highly unlikely, and at least in our approach, this will lead to immediate contradiction with experimental observations. Let me just use 2 minutes to say a word about continuum states. There are 2 ongoing, one proposal and 1 ongoing experiment to measure a continuum state in a 3-body system. One, this E217 JLab experiment is aiming at measuring the lambda and n system, and there is another experiment trying to measure this hypertriton with j equal 3/2. Of course, these are non-bound states, these are continuum states, and to measure, sorry, to calculate and predict the properties of this system is way more complicated than the bound state calculation which I've shown you. However, I will not be able to cover this topic, and hopefully Martin at 11 will give you a very nice introduction and result regarding our predictions for these experiments. Let me conclude now. We have presented an effective field theory based only on baryons, which are lambda and nucleons, to describe light hypernuclei. We found that it is possible to describe in this theory all the S-shell hypernuclei in a very nice way. Admittedly, we have a lot of free parameters, and I would say that our strongest or only prediction is this lambda helium-5. We have a prediction that double lambda helium-5 is solidly bound. Hopefully this will be measured one day. We find the neutral system, we predict them to be unbound, and this lambda helium-4, hydrogen-4 is probably unbound, but here this is on the threshold. It is more difficult for us to make solid predictions. So let me finish here. Thank you very much for listening and following this talk.
Thank you very much. Thank you, Neil, for this very illustrative talk with the problems and difficulties of building these effective field theories and leading to very nice predictions of the binding energy of hypernuclei. I don't know if, yeah, we have already one question by Laura, please.
Hello, thanks, Neil, for the talk. I have a questions concerning let's say, upper limit, the usage of the upper limit measured by Alice, because in our work, the upper limit for the binding of lambda is 3.2 MeV. The error is sizable, but the average value is not 6 or 7 MeV, but 3 MeV. Now, if you would take this value, this central value, as a constraint, as an experimental constraint into your theory. So, you know, in this work, exactly here, we also provide an upper limit for the binding of 2 lambdas, for the H-dibaryon, basically, right? Of 3 MeV. If you would use this as a constraint, would it change now prediction for hypernuclei or double lambda hypernuclei?
Actually, this is a very good question. we didn't try to check what are the implications of this upper limit. I think it would be very interesting to try that.
Yeah, because you know, this system that it was measured with correlation is the only system where you have really the interaction between two lambdas alone, let's say. And I was thinking whether maybe you can have a look and see whether if you use this 3.2 MeV with errors, right, which are of the order of 1.5 MeV, both systematical and statistical error. There are asymmetric, but you can look in the paper. Would be interesting to see whether this, let's say, impact or then on your prediction. Okay, thank you.
I'm sure it will have tremendous impact on our predictions. I'm sure for the
I'd like
5
to make a
and
comment.
4 body double lambda, yeah, it will have a huge impact. I think that we should try and address this question. Yes?
I think
I'd like to
Abraham
make a
also wants to
comment.
comment.
Laura, many years ago, when I worked with Philippine, we did a simple exercise. We increased the lambda scattering length from the value that we used then, something like 0.8 or 1 Fermi attraction without bound states. We increased it, and in a 3-body alpha lambda calculation, we got overbinding very quickly from the Nagara. Okay, so you don't have even to go to a bound lambda. When you increase the lambda strength and still the lambda is unbound, you will get overbinding for lambda helium.
Our scattering amplitude is, as it is written here, A0 is lower than 0.5. I mean, we have a small, we measured also a limit for the A0, so for the scattering amplitude, and is actually going exactly in the opposite direction. So less binding, if you want, a shallow interaction.
I'm not sure about the science, but do you imply that you may have a bound lambda system?
Yeah.
I mean, it is either a shallow lambda interaction compatible with hypernuclei experiments, actually, so with double hypernuclei, or is there is still a little room for a bound state. So we cannot distinguish between the two scenarios. But we can provide, in case you have a bound state, the upper limit for the binding, which is 3 MeV. So somehow, I mean, I was thinking that both these, let's say, assumption maybe can be tested within the theory that then makes prediction for hypernuclei. So.
Okay, I think I have to interrupt you. So I think the point is clear, and I think we have also to address other questions by Benoit. Sorry. There is also another hand raised. No questions?
Yes, I have a question here.
Yep.
Or a comment.
Please go ahead.
Yeah. My comment is, it is known that in the lambda problem, there is a sigma conversion. So I guess this process of sigma lambda sigma conversion is hidden in your constants somehow.
Yes, exactly.
Okay.
This is what. Let me go. No, I went the wrong direction. This is what you see in this diagram, that this lambda sigma conversion is buried into this coefficient. This is the way the theory works.
Thank you.
Welcome.
Can I make a very short question, Otan? Have I one second?
Very short, because we are already late. Yeah.
Nir, we are studying the possibility to investigate 2 and 3 body interaction of sigma 0 by exploiting hyperon formation in nuclear medium, so like a kind of final state interaction. But we verified that so the scattering would happen at energies at momentum, let's say, of about 500 MeV of the hyperon. Could these be interesting, important constraint for your calculation?
I think that the theory that we presented here is limited to low energy, and I'm afraid that it will be difficult to us to utilize it as the theory stands. To utilize such data, I think that we will need to adopt, and anyway, this is one direction we will need to go anyway, more elaborate theory, which includes also the mesons, the pions, and the sigma explicitly, and then we will be able to use it, but this is not in the current framework that we are using.
Thank you.
Okay, so thank you very much, Nir, and I think we should proceed now to the second talk that is more on the experimental side, let's say, of new methods to address this hypernuclei by Take Saito. So
yep.
You can go ahead. We now see your slides, so
okay, good.
It's all yours. Yeah.
So okay, thank you very much for inviting me to this conference. So I would like to present how we challenge the puzzle of the right hypernuclei, namely on the hypertriton, and also the state of the two neutral and lambda hyperon by means of the heavy ion beams, nuclear emulsion, and machine learning. So we are running the hypernuclear studies with heavy ion beams bombarding at the stable, fixed target since 2006. So we started the HiFi project at GSI. So there we put the heavy ion projectiles on the target, and then on the projectile spectator of a fragment, so we make the capture of the lambda hyperon from the hot participant zone, so we can produce the hypernuclear in flight. So therefore, we have a forward Lorentz boost of the hypernuclear event, and then decay particle from the decay of this hypernuclear field somehow concentrating on the forward directions. So therefore, we just to make the forward spectrometer, and we want to measure the hypernuclear decay. So because of the nature of the projectile fragmentation reaction, so we can also produce neutron-rich or proton-rich hypernuclei in principle. And also when we go to the higher energies, so we can also produce the hypernuclei with multiple strangeness. So this is the concept of the experiment. So we performed the first experiment, so-called HiFi phase 0 at the GSI. So the experiment was taking place in 2009 and 2010. So we bombarded the lithium-6 primary beam at 2 GeV per nucleon, bombarding on the carbon target. And we implemented this kind of a forward spectrometer setup with the big dipole magnet, so-called ADADIN. And then we aimed to measure, produce and measure the hypertriton and also the hydrogen for lambda by looking into the pi minus mesonic weak decay channel. So the experiment was successfully performed, and we had these outcomes from the experiment. And then I just want to highlight two of the outcomes of our experiment. And the first one was that we observed sort of the bump on top of the deuteron pi minus, in the deuteron pi minus and the triton pi minus invariant mass distribution on top of the big background distributions. And we somehow concluded that this may be a signal indicating the bound state of two neutral and lambda. So we published in the Physical Review C. But all of the theoretical calculations are giving the negative result for this bound state. So the second outcome from the HiFi experiment was to indicate the short lifetime of the hypertriton. So the hypertriton has been understood as the lambda hyperon is weakly bound to the deuteron core with the very small binding energy of 130 keV per nucleon, 130 keV. So this value was coming from the old emulsion data. And because of this weakly bound nature of the hypertriton, so it was regarded that the hypertriton lifetime should be very similar to the free lambda hyperon lifetime, which is 263 picoseconds. However, we observed shorter lifetime. And later, STAR and ALICE collaborations also measured the hypertriton lifetime and also indicating the short lifetime. However, at that point, so there are no theories to reproduce the short lifetime of the hypertriton because of the weakly binding nature of the hypertriton. So later, the STAR and ALICE collaborations updated the lifetime value. So STAR lifetime value goes smaller, and ALICE lifetime goes to bigger, and our lifetime is just standing in between. So therefore, we don't have any conclusion for the hypertriton lifetime experimentally. So therefore, what we want to do is that we really have to measure precisely the short lifetime of the hypertriton, and we also experimentally confirm whether or not the NN lambda bound state exists. So now, okay, so now, so so hypertriton lifetime is somehow getting the hot topics for the theory and also the experiment. So here, I just want to show one of the most recent results from the STAR collaboration on the hypertriton lifetime. It was presented in the Reimann Payer web seminar on April 22nd this year. So they are now deducing the long lifetime of the hypertriton, which is somehow similar to the ALICE data. But I have some remarks on this one. So now to get this lifetime value, so their experimental setup is defined from the former STAR experiment. So now they perform the fixed target experiment. So they bombarded the gold beam on the gold fixed target there. And they are producing the hypernuclei at the mid rapidity region, but they are still boosted, and they reconstruct the hypertriton mainly by using the TPC data. So now I just want to compare the relativistic heavy ion collisions, which was performed for STAR and ALICE, and also the fixed target heavy ion collision, which is for HiFi or the latest STAR experiment. For the relativistic heavy ion collisions, so we have a penalty factor for forming heavier fragments and clusters. So therefore, when they are measuring the hypertriton lifetime of the yield of the hydrogen 4 lambda is much smaller because of the penalty factor. But for the fixed target heavy ion collisions, since we produce the projectile fragment and they capturing the lambda into the fragment, so we can also produce variety of hypernuclei, and also the yield of the heavy hypernuclei and also the light hypernuclei sometimes is very similar. For example, for the HiFi phase 0 experiment, the cross section for the hypertriton was about 4 microbarn, and for the hydrogen 4 lambda, it is about 3 microbarn. So in the latest study experiment, so then they also observed the many hydrogen 4 lambda, and they also in addition to the hypertriton. So because they do the fixed target experiment. And this we have to be careful because so since hydrogen 4 lambda is so much populated, I also suppose that the helium 4 lambda should be also produced. Actually, they try to reconstruct helium 4 lambda by pi minus helium 3 and proton reconstruction. And this we have to be careful for this free body decay channel. So here I just want to show one example. So helium 5 lambda has only the free body decay channel going to the pi minus helium 4 plus proton. So, and then so here I'm showing the pion kinetic energy distribution coming from this old publications, and you can see that the peak or peak structure in the pion kinetic energy distributions. If it decays to the free body in the phase space, there should be no peak structure, and this should be widely distributed. And what is happening inside of the helium 5 lambda is as follows. So from the helium-5 lambda. So lambda make the quasi-free lambda decay, and then it comes to the pi minus, and also the strongly correlated pair of the proton and helium-4. So this means that it has sort of the via the two-body decay, helium-5 goes to pi minus and strongly correlated this one. So this I just put lithium-5 star, and coming to the pi minus, helium-4 and the proton. So this is just dissociated to helium-4 and the proton. So with this process, so they are remembering the two-body decay kinematic. So therefore, if we miss the proton, but just constructing the pi minus and helium-4, but the peak will appear in the invariant mass of the pi minus helium-4. So that's the reason why when in the pion distribution, so there is sort of the peak, it is indicating that it comes to this quasi-two-body decay channel. And this could be similar for the case of the helium-4 lambda. So there should be the quasi-two-body decay pi minus and helium lithium-4 star. Okay, this is the strongly correlated proton and helium-3, and coming to the three-body channel. And then if one gets this one, and this could be the contamination to the hypertriton reconstruction with pi minus and helium-3. And then if this is mixed into this channel, and then since the lifetime of the helium-4 is about 250 picosecond, which is similar to the lambda hyperon lifetime. So if there's a contamination like this one, then of course lifetime becomes longer. And also it is very now complicated, and we have to be very careful because with gold beam on the gold target, and then we can also produce the other heavier hypernuclei. They actually already tried to reconstruct the heavy hypernuclei, but all of the channel involving pi minus and helium-3 comes to this kind of contamination. So therefore, it is very hard to measure the lifetime or really resolve this contamination from the signal. So this is the reason for the hyper experiment and the coming WASA-FRS experiment. When we study the three-body or four-body hypernuclei, we try to use the very light beams like lithium-6. So, but I just want to come back to this slide again. For these two values, so since they made the hypertriton by using the relativistic heavy ion collisions, so there's no contamination, almost no contamination from the four-body hypernuclei. So therefore, for these measurements, there should be no problem with the contaminations. So now I just also want to come to the issue of the hypertriton binding energy. So the STAR collaboration also did excellent job for measuring the binding energy of the hypertriton. And then the error is somehow large, but they observed the higher binding energy than the formerly known the hypertriton binding energy. So now it is also the puzzle. And then also recent theoretical works by the Abraham and his colleagues are also showing that the lifetime of the hypertriton and also the binding energies are somehow strongly correlated. And also the other recent theoretical works also did study the hypertriton lifetime by using the effective field theory. So they found that not the lifetime, but this branching ratio or the ratio of this width, decay width is sensitive to the binding energy. And also for the NL lambda state, so also the pion-less effective field theory was also applied. So now, so also in the theory side, we are also trying to solve the hypertriton and NL lambda puzzle. So the experimentally, so lifetime and the binding energy of the hypertriton is not conclusive. And we also do not know if the NL lambda really exists or not experimentally. So therefore, with our project, so we want to measure the lifetime and the binding energy of the hypertriton very precisely. And we also want to confirm if NL lambda state really exists or not. So now we are now preparing the experiment at the GSI. So this is the new experiment. So with the new experiment, so we want to use the fragment separator at the GSI to measure the decay residues of the hypernuclei. So actually the FRS is usually used for producing the rare isotope beams, but we want to use this FRS as the forward spectrometer with very highly resolving power. So our idea is as follows. So we deliver the beam from the accelerator and then transferred to the mid-focal plane of the fragment separator there, and we want to produce hypernuclei such like these. And then we measure the pions from the decay of these hypernuclei in the same area, and then those decay residues are transported to the second half of the fragment separator, and we can measure the momentum with this excellent resolving power of 10 to minus 4. And for the pion measurement, we also need the large acceptance, much larger acceptance than high-fi, and we also need the reasonable momentum resolving power for the pi minus. And we are also requiring the large acceptance for the charged particles, including protons. So our choice to measure the pions in the mid-focal plane of the fragment separator is to employ the central part of the WASA detector, which was used for the hadron physics experiment at the Koji accelerator in Jülich Institute in Germany. And we want to move this one to GSI and putting into the fragment separator. And then we want to implement this kind of setup in the mid-focal plane of the fragment separator. So we have already made the proposal to the GSI PAC. And for the hypernuclear part, so it was already approved in 2017 with the highest grade A. And also last year, the experiment for the eta, studying the eta mesh nucleus by using the same setup was also approved. So now we are preparing for the WASA experiment. So now the WASA detector was already moved to GSI in 2019. And then we are trying to make this kind of setup. So this is the WASA superconducting magnet. And inside we have a Jewish chamber and also the time of flight barrel and also the end caps. And we are also now newly developing the scintillating fiber detectors for the hypernuclear measurement. So now the commissioning of the inner Jewish chamber inside of the superconducting magnet was already completed. And the superconducting magnet was already down to the 4 Kelvin temperature. And we are now upgrading the time of flight barrel surrounding this Jewish chamber. And we have already developed scintillating fiber detectors and also the electronics. And we are now constructing the holding structure. So we also developed sort of the inner scintillating fiber detector inside of the magnetic field like this one. And this is actually the additional detector after submitting the proposal. And we are also now upgrading the end cap detectors composed by the plastic scintillators. And also for the data analysis, we developed the machine learning model with GNN for measuring the pi minus track with the WASA detector. It is already completed. And we are now writing the publication for this method. So now I'm coming to the expected result from the WASA-FRS experiment. So we are expecting this kind of invariant mass distribution with the measurement of 4 days. So the mass width is about 3.2 MeV, which is much better than the hi-fi measurement. And the significance of the peak could be 120 sigma. So therefore, we can also study the NN lambda state if it's really there or not with the large significance level. And we also estimated our accuracy for the lifetime measurement. And we can measure the hypertriton lifetime with 8 picosecond accuracy. And then, so we are now preparing for the experiment. And the experiment is already scheduled to be performed in February to March in 2022. So we are somehow very busy for preparing for this experiment. So now I'm coming to the binding energy of the hypertriton. So for the binding energy of the hypertriton, so we are now analyzing the nuclear emulsion data from the J-PARC E07 experiment. So this was to search for the double lambda and the cascade hypernuclei by using so-called the hybrid method. So in this method, so they have the emulsion plate in this module, and this is sort of the moving because, you know, if the to avoid the beam of the intense beam on the one spot of the emulsion. And how they did was that, okay, they have a K minus beam and producing cascade minus hyperon in coincidence with the production of the K plus. So this is also measured. And they track the Xi minus by the other detectors composed by silicon strip detectors. And they estimate where Xi minus is entering on the emulsion sheet. So they know the entrance point of the Xi minus into the emulsion sheet, and they scan the nuclear emulsion only around this tiny region. And they can really reduce the human load for the nuclear emulsion analysis by the human eyes. And then they have observed 33 candidates for the double strangeness hypernuclei, but they could identify so far only one double lambda hypernuclei and one cascade hypernucleus. And already the analysis was already completed, so we could not increase the more statistics and also the systematics. But inside of the emulsion sheet, so there should be non-triggered events also for the double strangeness hypernuclei, and it is expected to be around 1,000 double strangeness hypernuclear events in the total of the 1,000 emulsion sheet, but they are not triggered. And also there are millions of single strangeness hypernuclear events should be recorded. So if we scan thousands of this size of the emulsion sheet entirely so we call overall scanning method, and then in principle we could discover all of the events associated to the hypernuclei. So now, so the emulsion is sort of the three-dimensional detector. So by changing the focal plane of the microscope system, we can also track the charged particle in the three-dimensional way. And then we can somehow save all of the images when we change the focal plane, and then we can analyze the data. But to do this, if we scan the entire one sheet of the emulsion, and then we have to analyze the 10 million images per emulsion sheet. And the data size for one emulsion sheet is about 100 terabytes. So we have about 1,000 emulsion sheets, so therefore we have to analyze 100 petabyte data. And this is not possible. So if we use our current technique to analyze those data with human eyes with 10 people, then we need 560 years to complete the analysis. But when I got a position at RIKEN a few years ago, so I somehow realized that this one can be sort of the good case for the application of the machine learning. So therefore, I started some projects to analyze the emulsion with machine learning. And we want to get the 1,000 double strangeness hypernuclear candidates, and also with the machine learning technique, so we can decrease the human load. So therefore, we are now trying to make this period much, much shorter to be 3 years. So the goal of the project was to really to discover the 1,000 double strangeness hypernuclear candidates. So we started the project, seriously the project and the development in April last year. But then we saw this paper for the hypertriton binding energy. And we also got huge interest, and also, this was also measured by the emulsion. And emulsion really can give the very precise information of the binding energy. So therefore, we somehow postpone for the double hypernuclear, but now we are concentrating on the hypertriton detection and measuring the binding energy by using the data of the nuclear emulsion. So first, so we don't know if we can really use the machine learning for the emulsion data. So therefore, we started with the simple case. So inside of the emulsion, so we have alpha decay events. This is the trium chain. So therefore, we try to, and we also already have some data which can be used for the training for the development of the machine learning. So therefore, we try to make the machine learning model to detect the alpha decay chains, and then it was already completed, and we already published in this year. Then now we are starting for the detection of the hypertriton events. And the difficulty is that we have no training data because we don't have any hypertriton event from this emulsion. But we need the training data for the machine learning development. So therefore, we made the Monte Carlo simulations, and we also used the GAN technique of the machine learning. So what we did was that we created the Monte Carlo simulated hypertriton production and decay. And then then we propagate into the emulsion in the Monte Carlo simulations, and we get some particle track data. And with the GAN technique, we converted or transferred image from the Monte Carlo simulation to the similar image to the nuclear emulsion, and we also mix the real background. So then we can make the sort of the training data, and we develop the machine learning model. And for the hypertriton event detection, so we use the Moscow CNN. So we also developed the model by using this framework. This is for the object detection. And then we try to detect the hypertriton events, so coming from somewhere.
2 minutes now, sorry.
Yeah, okay, and stopped, and then decaying to helium-3 and pi minus. And then, so this is sort of the Hammer event, and then we try to detect this kind of Hammer event and do the analysis. So this development was already completed, and we could already discover the first event of the hypertriton. So K minus B or K minus coming from somewhere is stopped in the emulsion, and then producing a hypertriton and decaying to helium-3 and pi minus back to back. And this is already guaranteeing that we can really measure the hypertriton binding energy when we accumulate more statistics. So we have already discovered 4 hypertriton events and 16 hydrogen 4 lambda events. And for those, we have already deduced the binding energy. So we also made the local emulsion, density calibration, and so on. And so when we accumulate 100 events, so we can achieve 50 keV binding energy. So this should be coming, I must say, within this year or next year. And then if we analyze the whole data, and we can also achieve the 5 keV binding energy accuracy for the hypertriton or binding energy information of the double or single strangeness hypernuclei. And we also estimated the systematic uncertainty for the binding energy measurement with the emulsions. And so we are also publishing this one. So now we are proceeding for the detection of the hypertriton and also the deducing the binding energy. And then after we complete this one, so that we also come for the helium-4 lambda binding energy measurement, which is very important for the charge symmetry breaking. And then we proceed for detecting or discovering the third and double hypernuclear candidate. And we are also proposing a new experiment at the J-PARC. So this is the summary. So with the WASA-FRS experiment, we are aiming at achieving the lifetime accuracy of 8 picosecond. And we also want to confirm if the NL lambda state exists or not. And for the binding energy of the hypertriton, so we do this precise measurement by using the J-PARC E07 nuclear emulsion and also the machine learning. And this is the collaboration for our project. Thank you very much for your attention.
Thank you very much for showing us this really nice prospects. And we already have one question by Laura. Please go ahead.
Hello, hi Take. Thanks for the very rich, let's say, talk. I have a comment about the measurement of the hypertriton lifetime. As far as the ALICE measurement is concerned, I can tell you that this two-body background coming from the A=4 hypernuclei, the two-body channel, has been considered and it is negligible for two reasons, mainly because of the penalty factor you also mentioned. Yes. And hence there is always a factor 1,000 basically whenever you
exactly, yes.
And hence is really not contributing, and it has been really looked into, and we think that we do not have that. So as far as the ALICE measurement are concerned, for us the puzzle is solved in a sense that the measurement that we have now, which is about 90% with respect to the free lambda lifetime, seems to be, let's say, already converged values. I don't know how much now this background you mentioned impacts the fixed target results from STAR, but I just wanted to mention that in ALICE analysis it has been considered, it's not impacting at all.
Yes, that's the reason why here I'm also putting that no such contamination for the ALICE and the STAR, especially for the STAR format measurement, so they have no problem for this kind of contamination.
Yeah, but
so
they had other problems in their measurements, and that's why also when okay, but this is something else. I had then also another question about the binding energy measurement, whether you also, because I could not understand whether you want to look only at the three-body decay or also at the two-body decay.
Okay, first, so for the hypertriton, first we look into the two-body decay. So because we have already developed the model like this one, but of course we will also look for the three-body decay in near future. So we are already starting the development of the machine learning model to detect the three-body decay, because we also, not only for the hypertriton, we also want to measure the helium-4 lambda, which gives only the three-body decay channel, no two-body decay from helium-4 lambda. So therefore we are now working. And then I also just want to come back to the hypertriton lifetime puzzle. So as you said, and as I also mentioned, that these two measurements from STAR and ALICE by using the relativistic collisions, I must say very clean, because we have no contamination. But I'm still puzzled why the STAR value and ALICE values are so much different.
Yeah, because
so
but because there are some issues, non-treated issues in the STAR analysis, which meanwhile they have maybe been improved. But okay, but this I cannot, I say.
Yeah, but they have actually they have more statistics. They mean the STAR, and they also look into the three-body decay. So I also hope that ALICE can also look into the three-body decay for the hypertriton lifetime, and then ideally just want to see the difference. And at the meaning time, so we also try to measure the hypertriton lifetime with a different method. This is fixed target with the lighter projectile. So we are really complementary, but I think we need all of the effort to be able to conclude hypertriton lifetime. So this is just my impression.
Sure. Thank you, Take.
Yeah, thank you very much, Laura.
Laura. I don't see any other raised hand. I have a question myself. Is this the first time that in emulsion analysis is used the machine learning techniques?
Actually, for the other emulsion experiments, actually for the neutrino measurement, actually the particles are penetrating perpendicular to the emulsion sheet. So they also tried machine learning.
But did they have in this situation an input for the Monte Carlo, or they have to build it in the same way?
No, they have not done this one. So okay, so with the Monte Carlo simulation, this is the first case.
Okay. Good, very good. It will be very interesting to see how this works. Okay, we have another question by you. Please be very, very, very short because really we are running out of time.
Hi, you said that inducing lithium-9 could reduce the contamination. Could you please a little bit elaborate on that, please?
Actually, you mean the discontamination issue, right?
Yeah.
This is somehow very hard to evaluate because it really depends on the cross section, and it also depends on how much the other hypernuclei produced. For the HiFi case, so we use lithium-6 beam and we evaluate also the contamination, and then so for our case it was negligible, and also it is also depending on the acceptance of the detector. For our case, so we have a discontamination, but this is not overlapping to the hypertriton peak. So, and we don't have so much heavier contribution because we use lithium-6 beams. But for the case of the STAR experiment, so they smash the gold beam on the gold target, therefore they can produce tons of the heavier hypernuclei. So I don't know how much contamination they have, but they have to look for each species very carefully. Otherwise, the lifetime value could give some misleading.
Okay, thank you very much.
Okay, thank you very much. Thanks to Take-san, and I think we can go to the last talk of this morning session by Abraham Gal. So, yeah, we see you, and hopefully we see your slides, so please go ahead. There you go. Yeah, we see your slides. So please, Abraham, the stage is yours.
Can you hear me?
Yes, perfectly.
Okay, so I will talk about cascade minus P going to lambda lambda, which is what we call capture in light emulsion nuclei as a means of constraining the cascade nuclear potential. This is based on a work that Ellie Friedman and I put on the archive and submitted for publication. And I read from the abstract in a kind of revised version. All 5 K, and J-PARC two-body reactions, capture events, these are, the two-body means that we have only 2 single lambda hyperfragments here at the final stage. All of them are considered, and they all happen to be capture from 1p cascade minus nuclear states. And when we analyze it in terms of cascade nuclear potential, the potential is strongly attractive with a nuclear meta depth larger than 20 MeV. So let me now go to the next. So my talk is divided into 2 parts, brief parts. The first part is that I give you a brief overview, mostly experimental. And these experiments from the 90s, the end of the 90s, are counter experiments that were done in KK and in Brookhaven on carbon-12. And you see here the tip of the quasi-free excitation. The scale here goes according to excitation energy of the psi. In this process, a proton converts to psi minus. And there are some fluctuations here. The resolution is pretty bad. one cannot claim bound states. Perhaps it's wishful thinking to see a bound state here or there. And estimates from analyzing this tip of the quasi-free give you weak psi in nuclear matter, or so in carbon of order 15 MeV. I go now to the next picture from the same period. This is Brookhaven AGS 906 on beryllium 9. They were searching for stable lambda-lambda hypernuclei below beryllium, and they claim to have found lambda-lambda H4, about which Nir Barnea talked today and mentioned that it's unlikely to be bound. Now, this is analysis of the full quasi-free excitation by Harada and Irabayashi of this year, and they conclude somewhat larger value for the cascade potential depth, which is 17 plus minus 6 MeV. Yet, we don't have psi minus bound state smoking gun from these experiments, and we await J-PARC final E05 and future E70 results for a dedicated K minus K plus experiment on carbon-12 and perhaps on lithium. On the theoretical side, I show here a slide from Hiyama et al., PRL, that studied cascade hypernuclei candidates in few body systems. The substantial model dependence. This gives you the phase shift in a Nijmegen version from 2008. We have more modern versions now. And this one shows a recent Hull QCD, lattice QCD, that uses quite physical pion and kaon masses. And you see there is a big difference. For example, if you take the spin and isospin 0 channel given by red, the phase shift here is large, and positive means an attractive potential. Here, it's negative means negative repulsive potential. This big difference is due to the point of where this H dibaryon, or kind of coupled channel effect between lambda-lambda in the singlet state and cascade N lies, whether it's above the cascade N threshold or below. Now, theoretical manipulations on these phase shifts doing geometric calculation published recently gives us very shallow cascade nuclear matter potential. So we have a puzzle here. The most recent and perhaps trustable theory gives us something quite small for the cascade, whereas experiments show us that it's probably between 10 to 20 MeV. And the fact that the Hull QCD is a good solution theoretically was shown by Ellis' recent femtoscopy study of proton psi minus correlations. And you see here that their measurement, this is Coulomb plus Hull QCD, and the data points are very closely go through or near the Coulomb and Hull QCD. Just a side remark is that ESC 16, the Nijmegen latest version, is doing very poorly. It's actually repulsive. So I say yes for attractive Hull QCD, no for repulsive Nijmegen potential. So this is kind of background data. And now I go to K minus K plus, not in counter experiments, but in light emulsion nuclei, where the psi minus is being produced in this reaction and stopped and captured. So first, let me show you once more, after so many demonstrations, the Nagara event. The Nagara event was established firmly by showing a cascade minus stopping at vertex A. The vertex A is here. Then something moves to B, and then vertex C. And the three vertices are given here, A, B, C. The first one is atomic capture, which is verified by kinematics to be from the 3D atomic orbit. This is the last orbit that will be seen probably in the atomic cascade of cascade minus. And all particles here are observed. You see tritium and alpha, so you know that you produce lambda helium-6, which is verified by the decay, because this is unique again without neutrons or unobserved particles. So it doesn't matter that the next decay of lambda helium-5 involves unobserved particles, because you already, the kinematics is quite restricted and consistent for the capture and decay. So I'm looking to events like this in twin lambda, capture and decay vertices. So I give you an event that I will accept, an event that I tend not to accept, include or exclude. This is a recent event published by the J-PARC E07 in PRL recently called Ibuki. And capture is to two hyperfragments. One of them, lambda helium-5, is uniquely identified by its decay mode. So it doesn't matter much that lambda beryllium-9, lambda beryllium-10 is not fully identified, because there are neutrons sorting around, because this one is in the decay scheme is observed, and the capture is the two-body. So that leads to determination of the binding energy of the cascade minus, which is found to be likely in a 1p orbit, below what one thinks about in atomic states in the atom. Kinka put here in this publication, I'd like to exclude it because there's no vertex, whether it's capture or either of the decays, that is free of neutrons. So nothing here is really unambiguous. So I'm afraid that perhaps there are other options. I don't know. I don't say this is not the right interpretation, but I would not like to base my arguments on this event. Moreover, this involves then, if done correctly, production from a cascade bound state around 6 MeV, which is a S state, and the capture rate for capture from one S state compared to 1p state is only a few %. If you look to the number of events they have in emulsion and the number of events they estimate they generate in total, it's very unlikely that they can observe capture from 1S. So I go now to a full list of the 5 events I was able to find in the literature for two-body cascade minus capture emulsion events. 3 of them go back to E176, which is experiment done in the beginning of, in the 90s actually. And 2 more events, one Ibuki I mentioned already, and Kiso. 3 events are on carbon, and 2 events are on carbon, 3 are on nitrogen. The 2 events on carbon gives you the same binding energy for cascade minus and somewhat larger value for events on nitrogen. These binding energies are considerably larger than the atomic 3D state. Now, there's old work that observed that in order to publish, to form 2 lambda, single lambda hypernuclei, where the lambda is in the 1s channel, you need to form the 1s lambda squared configuration. In this short range reaction, you need to have the capture angular momentum and the capture of the proton on which the capture occurs to be the same. So in the P shell, it means that the L of the cascade should be or must be the P state. And all these things mean that a P state is around 1 MeV. It's already developed from a 2P atomic state. Capital letters mean atomic state, small letters mean nuclear state. So it's developed to be bound with the help of Coulomb-assisted state to be there. Okay, so Ellie and I did a complete calculation of the atomic cascade in carbon-12. And the 3D state is around here. It's bound by a little bit over than 100 kilovolt. And what I show here is the two lowest P state, 3P and 2P. So the 3P state is here near the 3D. And as you increase the strength of the optical potential we use in the form of a density, this 3P goes towards becoming 2P. This is a rearrangement effect. The 2S, which is in red here, goes to become the 1S. But the 2P state goes and then dives strongly to become a nuclear state, 1P, and the 1S atomic dives already quite early to become a nuclear state. So if I confront this, this motion of the states with the experimental window of 0.82 MeV observed for the twin lambda hypernuclei, you see that it gives me a range of values for the strength of the optical potential, which is real B naught, 0.32 plus minus 0.01 Fermi. This is something like the scattering length of the system. And this translates into this nuclear matter depth for the cascade. However, it would fail in nitrogen-14. Why? Because when we calculate nitrogen-14 with this parameter for the optical potential, we don't get the observed, the experimental binding energy of the Ibuki and the Kiso event, but we get something larger by 1 MeV. So what's happening here? The resolution is very simple. Nitrogen-14 is not spin zero nucleus. And when you couple a P cascade to the ground state of nitrogen-14, 1 plus and 1 minus, you have 3 states. So there is a quadruple interaction which arises naturally in a shell model description. And when I take care of that with a strength that is compatible with the strength for the monopole part, with the strength of the potential, I get this splitting here. And one of the states, the 0 minus here, has a binding energy which is compatible or agrees with what I need to calculate, with what I need to obtain for nitrogen-14. So in fact, doing nitrogen-14 on its own is not enough. You have to combine it with carbon-12. The extraction from carbon-12 is model independent, considerably more than from nitrogen-14. This picture is the one before last I have. This shows you a similar situation that Dover and Milner and I encountered in a work where we try to interpret a lambda carbon-13 spectrum produced in a K minus pi minus reaction in Brookhaven. And in the beginnings of the 80s. And there what happened was that one observed lambda carbon-13 states based on carbon-12 ground state and on the 2 plus excited states, first excited state. But instead of 4.4 MeV, they observed something 6 MeV apart from the ground state. So we realized that this splitting given by the QQ quadrupole potential leads to something that would correspond to this observation. Changing the angle of the phi minus in the experiment changes the nature of the state, and then it is observed with a large fraction below with 1.7 MeV apart. So these ideas of what to expect when a hyperon is coupled to a non-zero spin level were familiar to us from the lambda spectroscopy beginning in the 80s. So I come to a summary and outlook. I reached consistency among all 5 twin lambda two-body capture events. We get this value in nuclear matter. If we put Pauli correlations into the game, this reduces by 10% to 22 MeV, and we think it's pretty convergent there. We expect then from our calculations from this optical potential, the 1s state around carbon to be 10 MeV or even more. In nitrogen, perhaps 11 or 12 MeV, considerably more than the recent claim by the E07 experiment for states produced in the 1s that are around 6 or 7 MeV. So here we differ. This will have implications for dense neutron star matter, but one needs to have experiments in non-zero spin nuclei in order to generate the isovector part of the psi-n interaction. Before this is done, we can't go really in theory to neutron matter. So I thank Ellie, who was my partner in this project, and to all of you for attention. Thank you very much.
Thank you very much, Abraham, also for staying on time. And I don't know if we have some questions. I don't see any raised hands. So apparently everything was very clear. I have a question myself, and first obvious question that comes when you look at your results of this 24 MeV of this value of this potential for the psi minus, how this reconciles with the, let's say, validated lattice QCD calculations in vacuum by at least that provide a much shallower potential, right?
I can get this order of magnitude of potential from a very simple procedure that I tested it on lambda hypernuclei and gives there 30 MeV for the potential depth of lambda. It's not a complicated G-matrix calculation, which I cannot repeat or I cannot check really until I see the full detail. So far, I have not attempted to write it down, but I will soon.
Okay, thank you very much then. If there are no further questions, I think we can close the session for this morning. I thank very much the 3 speakers of today.